So here we are in section 7.3. We've got three objectives here. Use the product rule for radicals, use the quotient rule for radicals, and then simplify radicals. We're going to spend a lot of time simplifying radicals. So first off, using the product rule for radicals. Here is the product rule. Here's as if we have the nth root of a and the nth root of b, and they're real numbers. N is a natural number, and then the following holds. So if we have a set of radicals that have the same index, we can multiply them by multiplying what is underneath the radical. So this is what this is saying here. We got nth roots of a times nth root of b equals the nth root of a times b. And here it is. So the product of two nth roots is the nth root of the product. Now, may not make a lot of sense until we look at some examples here. So multiply, and so notice we have both of these are square roots, so this index is the same. So what I can do is multiply what is underneath the radical there. So I'm going to multiply 5 times 13, and I'm going to end up with the square root of 65. So remember, I keep it underneath the radical there. In B, we're going to use the product rule on that. We would take 7 times xy, and we end up with square root of 7xy. Once again, they're of the same index, so we can combine them in that way. Next is the quotient rule. We've used this before. When we've dealt with fractions. So if we have the nth root of a and the nth root of b, n is a natural number, the following holds. The nth root of a over b is the same thing as the nth root of a over the nth root of b. So this is really just a version of the quotient rule, right? We can break this up between the nth root of the numerator and the nth root of the denominator. So this one's a little bit more challenging to comprehend than the product rule. So let's look at some examples of it. So if we're going to simplify each one of these. So what we have here is the square root of 100 over 81. So what we do is we break that apart. So now we've got the square root of 100 over square root of 81. We just break it apart. Square root of 100 is 10. Square root of 81 is 9. So the square root of 100 over 81 is 10 ninths. Notice how we just broke it apart between the numerator and denominator. B will do something similar. We'll break it apart between the numerator and denominator. And something special happens in the numerator. So square root of 25 is easy to comprehend. We get 5. Square root of 11 is an irrational number. If we were to put that in our calculator, we'd end up with a non-repeating decimal, I believe. So now in C, notice we have an index of 3 here. So we're taking the cube root of the numerator and the cube root of the denominator. So the cube root of 125 is 5, but we can't break the cube root of 18 down. That would become a decimal, an irrational number. So we leave it in that form. So get used to leaving it in sometimes leaving these square root radical expressions in their form if they can't be broken down nice and neatly. We'll talk about how to break these things down here in a little bit. So now D is a little bit more tricky. We break it up in the numerator denominator. Okay, obviously we've got the square root of 16, but what we're looking for in D in the numerator here think about y to the 4 times y to the 4th, or the words y to the 4 squared. So what we end up, so basically y to the 4 times y to the 4th is y to the 8th, right? So we took the square root of y to the 8th, and that becomes y to the 4th over 16, square root of 16, which is 4. So another way to think of this is if you, one way to think about it is actually you're dividing this exponent of the variable by the index. The index here is 2, right? So what I did was divide y to the 8th. Well, I divided 8 by 2, and I got y to the 4th. So we'll look at e here. We break it up in the numerator and denominator. And as I said, one way to think about these is to divide the exponent of the variable by the index. Notice 2 can't be divided by 3, but 12 can be divided by 3. So I want to show you what happens. The cube root of x squared stays the same, but we divide the 12 by 3 to get 4. Another way to think of this is r to the 4th times r to the 4th times r to the 4th ends up with 12, right? Because we're applying the product rule where we add exponents. But just a quick way to think of this is to divide the exponent here by the index. All right, so here we are, objective 3, simplifying radicals. All right, so I'm going to take you through the conditions for simplifying a radical. This is the best place to start. Now, these conditions are going to be a little confusing as we present them, but I think they'll become more clear as we actually simplify these radicals following these rules. So the first rule is the radicand has no factor raised to a power greater than or equal to the index. The second rule is the radicand can have no fractions. So no fractions and no fractional radicands. And the denominator cannot contain a radical. And exponents in the radicand and the index of the radical have a greatest common factor 1. So, considering these rules, these are examples of radicals that have been simplified. These bottom ones are examples of radicals that are not simplified. So what I'm going to do is take us through each one of these cases and talk about why they're not simplified. So the first one is square root of 28. This violates the first rule. The radicand has no factor. Remember, the radicand can have no factor raised to a power greater than or equal to the index. So what we're going to do is break up 28 into factors. Notice we can break 28 into 4 times 7. Notice something about 4. 4 is a perfect square, right? The square root of 4 is 2. But think of it this way. This is the same thing as 2 squared. 4 is the same thing as 2 squared. What this is a factor raised to a power equal to the index. So what we do, we simplify this out into 2 square roots of 7. So typically this is what we do with these things. We break them up into factors, and what we're looking for is a perfect square factor. Then we take the square root of that perfect square factor, take the square root of it, move that square root outside of the radical. This is the way we simplify these things. This is something you're definitely going to have to master, is turning something like the square root of 28 into its simplified form, 2 square roots of 7. Now we have the cube root of 3/5. This violates the second rule. Remember, the radicand can have no fractions. We've got a fraction here. So let's break this up into numerator and denominator using the quotient rule. So we still, now this violates another rule. Remember, the denominator cannot contain a radical. So here's how we handle these things, and we'll talk about this more in later sections. But how we simplify these things is we multiply by a form of 1 here, which is square root of 5 over square root of 5. You see what happens in the denominator. Square root of 5 times square root of 5 is the square root of 25, which is 5. And then we use the product rule on the numerator by multiplying what is the radicands, because we've got the same index. So we multiply the radicands, and we get square root of 15. So we end up with square root of 15 over 5. So what we've done is this is how we simplify these things. The first being that we can't have any fractions. Then we have a radical in the denominator, and then we multiplied by square root of 5 over square root of 5, which is the same thing as 1, right? Square root of 5 divided by square root of 5 is 1. A number divided by itself is 1. This is called rationalizing the denominator. Square root of 5 is an irrational number. When we multiplied it by square root of 5, it became a rational number. We'll talk more about this later. Then we have 7 over square root of 7. This violates the third rule, where the denominator has a radical in it. So remember, we can simplify this by multiplying by a form of 1, which is square root of 7 over square root of 7. Notice square root of 7 times square root of 7 is 7. And then in the numerator, we end up with 7 square roots of 7. And these 7s are going to cancel out, so we're left with square root of 7. So this is the same number as this one right here, only it is more simplified. So in this case, you can see kind of why they prefer to not have any radicals in the denominator, because they simplify and look a lot neater. Now, again, what we did was rationalize the denominator and to end up in this simplified form of this number. Here we have one, the cube root of r to the 12th. This violates the fourth rule. Exponents in the radicand and the index of the radical have a greatest common factor 1. So notice we have a greatest common factor of 3 between these two things. So what we can do is, remember when we've talked about fractional exponents? Taking the cube root of r to the 12th is the same thing as taking r to the 12th to the third. Then we use the power rule here, multiplying 1/3 times the 12. 12 divided by 3 is r to the 4th. Another way to think of this is r to the 4th times r to the 4th times r to the 4th. That's that's we're cubing r to the 4th there. So we take the cube root of that, and we get r to the 4th. So one way to think of it is thinking of it in fractional exponents. Another way to think of this, and it's not the correct mathematical way to do it, but it does work, is if you have a variable raised to a power, and you can divide the power by the index, you can divide the power by the index, and you end up with r to the 4th. See, what we did was divide 12 by 3, and we ended up with r to the 4th. So based upon those rules that we just talked about, let's look at some of these. So first we have square root of 32. So the first question we have to ask ourselves, can we factor this in such a way in which the factors will be a perfect square factor? Now, if you think about it, we can actually make this into 16 times 2. And 16 is a perfect square, so we have a perfect square factor. So we found the perfect square factor. So now we take the square root of 16 and move the square root of 16 outside. But let's just break this up a little bit further. So this is kind of the reverse of the product rule of radicals, right? So now we've got square root of 16 times square root of 2, and so we end up with 4 square roots of 2. So we just simplified square root of 32. Just get used to the way that these things are supposed to be written. This is the way they're supposed to be simplified. So now we have 300, square root of 300. Now let's think about what would be a perfect square factor that would go into 300. Actually, if we think about it, 100 times 3 will work. And 100 is a perfect square factor, right? Because the square root of 100 is 10. So we just break this apart using the reverse product rule here. So we take the square root of 100, and we end up with 10 square roots of 3. So the square root of 300 must be written in this way as 10 square roots of 3. This is how we simplify radicals. So now we have square root of 35. So we've got to think about, are there any perfect square factors that'll go into 35? Our factors are 1, 5, 7, and 35. None of those are perfect square factors. So we can't simplify that any further. So it cannot be simplified any further. Now these next ones are higher order roots in simplifying. Now there's not going to be any of these on the test, but there are a couple of homework problems. So this time, instead of finding a perfect square factor, we've got to find a perfect cube factor of 54. This is a little bit harder to think about than the perfect square factors. But if we played around with 54 a little bit, we would see that we can do 27 times 2. And we know that the cube root of 27 is 3. So we simplified the cube root of 54 into 3 cube roots of 2. Now the ones in the homework are cube roots, but this one to E is going to challenge us a little bit more. So we got to think of fourth roots. So if you think about 3 to the fourth, 3 to the fourth is actually 81. So if we think about 3 to the fourth, 3 to the fourth is actually 81, and 81 times 3 is 243. So what we've done is broken this up into a fourth root. So this can be simplified into 3 fourth roots of 3. So now it gets a little more challenging when we start dealing with variables in there, variables raised to exponents. So the first thing we're going to do here is we're going to factor this p to the 7th. And in everyday language, what you do is factor it in such a way that the index, which is 2, will divide evenly into the exponent. So remember, we can't, so 7 here, we got 7, we can't divide 7 evenly by 2. So we factor that in such a way that we got p to the 6th times p. Now we can so we just kind of break this apart here. The p is going to have to stay underneath there. But we can handle 25, and we can handle this 6. Remember I said the kind of the shortcut to do this is divide the exponent by the index. So 6 divided by 2 is 3, and the square root of 25 is 5. So we end up with a simplified form of this, 5p to the third times the square root of p. So what we did was factor it in such a way that we could divide the exponent by the index. You can think of it this way. P to the 6th is the same thing as p to the 6th to the half. Remember fractional exponents? And that gets us to p to the third. Or you can think of it this way. P to the third times p to the third is p to the 6th. So we're taking the square root of this, and we get p to the third. So now we're going to simplify this one. Now, this is the same thing. 72 is the same thing as 36 times 2. They just wrote it as 6 squared. And notice what we do with this y to the third. We factor it in such a way so that we can now divide the exponent by the index. So this is going to turn into, and as I said in everyday language, factor in such a way the index will divide the exponent evenly. So we take out the square root of 36 is 6. We take out the square root of y squared. The 2 and the y and the x remain underneath the radical sign.